Hello everyone, welcome to today's live broadcast entitled IR Microscopy, Big Insights from Small Samples. I'm Jerry Workman, the Senior Technical Editor of Spectroscopy, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by Spectroscopy and sponsored by PerkinElmer. PerkinElmer is an American global corporation which specializes in the manufacture of analytical instrumentation used in testing of industrial, food, and pharmaceutical products, as well as environmental and biological samples. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the dock at the bottom of your presentation window. Before I introduce today's speaker, I'd like to ask our audience to participate in a brief polling question. Please click directly on the screen to enter your answers. Here's the question. What type of topics would you like to learn more about? Micro ATR and ATR imaging techniques? Evolved gas analysis using TGIR hyphenated technology? FTIR microscopy for microplastics analysis? Quantitative analysis with FTIR, or other? I'll repeat the question. What type of topics would you like to learn more about? Micro ATR and ATR imaging techniques, evolved gas analysis using TGIR hyphenated technology, FTIR microscopy for microplastics analysis, quantitative analysis with FTIR, or other? Thank you for participating in our poll. If you selected other, please specify what type of topics you would like to learn more about. Again, if you selected other, please specify what type of topics you would like to learn more about. Thank you for participating in our poll. I would now like to introduce today's speaker. We are pleased to be joined today by Ryan Smith, PhD. Dr. Ryan Smith is a senior field application scientist for PerkinElmer's infrared spectroscopy products covering the Midwest region of the United States. In this role, he identifies analytical solutions to help customers meet various challenges, as well as providing proof of concept and method development assistance. Thank you for joining us today. Dr. Smith, please get us started.
Thank you for the introduction, Jerry. I appreciate it. Hello, everyone. I'd like to begin by thanking you for attending today's webinar. I'd like to tell you a little bit about infrared microscopy, and in some respects, this technology is fairly exotic and is not necessarily as widespread as FTIR analysis in general. And so I would like to just share a little bit about theory of the measurement and where this technique is really critical in helping scientists answer some of the toughest challenges they face. So first, I'd like to begin with a little bit of an analogy here that oftentimes in life that our largest challenges are presented to us in some of the smallest packages, right? So on the left-hand side, we have the Rubik's Cube. This puzzle, this toy is actually available in sizes to a point where it's actually attached to a keychain and is portable. If you're a parent, of course, you'll appreciate the challenge that comes in the small package of a baby or toddler. And oftentimes, of course, there's a lot of adjustment which goes into the initial stages of parenthood. Last but not least, then, as scientists, oftentimes we're presented with a wide range of challenges in terms of samples. At the top, we see contamination, where a small amount of material is spread or diluted through a bulk material or material of interest. In the second example, we have foreign materials or defects which are distinctly embedded in that material. And thirdly, last, we see situations where it's simply that a small region of our sample is of interest to us. So this could be a coded device, maybe a small electronic package that we are trying to analyze. And I bring up these three examples here because I would like to draw some distinction that analysis of contaminants in examples where they are actually spread or diluted through a bulk material, these oftentimes require different analytical approach, maybe some added sample preparation or chemical workup to isolate that contaminant for analysis. Perhaps it requires analysis with an alternative analytical technique, perhaps chromatography or some other analytical instrument. For the sake of today's discussion and the presentation here, I'll focus more on the second and third examples here, where these are foreign material defects or debris which have been somehow isolated, perhaps embedded in a material, or there is a small region of interest on the surface of a sample. So if you have a fairly limited understanding of infrared spectroscopy as a technique, I would just like to do a brief, what you might call a crash course in vibrational spectroscopy theory. Oftentimes, vibrational spectroscopists will represent bonds in molecules with the analogy of a ball and a spring. So in this analogy here, the chemical bond and the atoms are represented by two balls connected by a spring, each atom being a ball, and the spring, of course, being the bond between them. So the masses of these balls at each end will change depending on the atom that you find, and the strength of that spring or that bond also changes. These are described by the force constant, K, and then the reduced mass, represented by the symbol mu, represents a combined mass of those atoms. And the frequency of that vibration then is represented by nu, calculated from those pieces of information. So to sum this up and how this is practically usable, the infrared spectrum provides insight into the types of bonds which are present in a sample. This information, taken in aggregate, a snapshot of the types of bonds which are present in a material, then give us insight into the identity of that material. So here's a quick example. I'll go through a manual spectral interpretation process. Now understand that when performing material analysis with an FTIR or an infrared microscope, that manual spectral interpretation is not always a requirement for material identification. In many cases, users will either run a comparison by calculating correlation between a known sample and the tested sample, or they will perform a library search, a sort of dragnet approach to the identification process. But here we'll go through an interpretation of the spectral features here manually. So generally speaking, the interpretive process proceeds from left to right on the infrared spectrum. So in the spectrum presented on the screen, the first peak that we see at left represents an OH bond in the material. That relatively broad but low intensity peak is representative of an OH stretch. Moving towards the right, we come across a collection of bands, and going even further from there, the leftmost of the peaks here represents an unsaturated carbon-carbon bond with a hydrogen attached to it. We're seeing the carbon-hydrogen stretch of an unsaturated system. In this case, moving towards the right, we see several peaks which provide added insight into the nature of those unsaturated bonds. That this actually indicates that there is a monosubstituted aromatic ring present in the sample. Going towards the right from there, we come across CH stretches and CH deformation, which represent saturated systems. So carbon-hydrogen stretches at the left. Towards the right, we come across carbon-hydrogen deformation vibrations. Towards the center of the spectrum, we see a very weak peak. This is a carbon-nitrogen triple bond here, or a nitrile functional group. Then towards the right of that, we come across a carbon-oxygen double bond, which is a carbonyl functionality. So in aggregate, the bonds that we see here are representative of a material which is acrylonitrile butadiene styrene polymer, or ABS, with some sort of impact modifier. So to help understand the need and benefit of an infrared microscope, I'd like to take a step back here and actually look at the infrared measurement process. And as we go through this process and how the measurement is actually performed, we can piece together the benefit and the need for the infrared microscope. So the first step in the infrared measurement with an FTIR instrument is background measurement. So the background measurement is measured in the absence of sample. The background measurement captures the infrared intensity versus wavelength or frequency. In this case, we're viewing a spectrum with intensity versus frequency in terms of reciprocal centimeters. The second step is the measurement, the very same measurement, except performed in the presence of the sample. So in this situation, with this analogy presented before you here, this is a measurement of a mineral spirit sample within a liquid cell. So at the right-hand side, you see that that intensity spectrum is very different, that there is now loss of light at certain frequencies, which are ultimately those spectral bands similar to what we observed in the previous spectrum. These two pieces of data are then ratioed. So that sample single beam spectrum is divided by the background single beam spectrum to present us with what we call a transmittance spectrum. So let's go to the next step in that measurement, or consideration of theory here. The infrared beam size in the Frontier FTIR produced by PerkinElmer is approximately 10.86 millimeters in diameter at 4 reciprocal centimeter resolution. So if we calculate the area of this infrared beam at the focal point, it's approximately 92.57 square millimeters. Now in a forensic lab, in a situation where they come across trace evidence on a routine basis, they may come across a sample of what is human hair. Now, it may not be immediately apparent that this material is human hair, and that's actually where the infrared measurement can be useful. So if this human hair is a typical width that may be about 70 microns in diameter, and if this is a small piece of human hair, it may be 0.5 millimeters in length, potentially a little larger. Now in this example, if the hair, if this piece of hair is 0.5 millimeter in length, the area that that hair would occupy is 0.035 square millimeters, so it's very small. This means if we were to try to put that human hair sample in that infrared beam, that human hair would only interact with 0.038% of the infrared beam. So I've done a sort of mock-up as to what that would look like, taking a spectrum of a human hair and scaling it to account for the small area that it would occupy in the infrared beam. Again, because our measurement is performed as that two-step process, and the ratio of intensity between those two steps is calculated representing the spectrum, then the intensity of light loss, or the change in light, is dependent on the area that the sample occupies in the infrared beam. So the spectrum before you effectively looks like a flat line. The intensity is extremely low, but let's zoom in. So here we see it from 0 to 100% transmittance, 100% representing zero loss of light. So now we're looking at a scale of 90 to 100% transmittance. Still effectively, this looks like a flat line. If we examine the spectrum with an even more expanded scale from 99 to 100%, we see some very weak spectral peaks. So it's clear from this that working with microscopic samples from a measurement perspective, let alone a practical perspective, it would be very difficult to get a high quality infrared spectrum from a small sample if there was no sort of collection and focusing mechanism to really focus that infrared light on the sample. And so that's where apertures come in. Apertures are simply devices which will block the infrared beam. So in this example here, we're looking at spectra collected with the material with large apertures at top or no apertures at top, and then with apertures down at the bottom. So in the top example, the infrared light goes through this sample in the analogy here being a 3-layer product, where we have 2 layers of polyethylene and 1 layer in the middle, which is polyethylene terephthalate. So as the infrared light goes through this sample, unrestricted, it can interact and be attenuated by each of those layers which is present in the sample. So the infrared spectrum that's measured at the other side of the sample is actually representative of all layers that the infrared light interacts with. Moving now down to the bottom example, we consider a situation where apertures are used to restrict that infrared beam. So now the light reaching the detector is only that light which has interacted with the central layer of the material, which in our example here is polyethylene terephthalate, and the spectrum that we measure on the other side of that material then represents only that layer in the center. So the use of apertures actually presents a practical challenge for the spectroscopist, in that apertures themselves are rejecting light. So we work with vanishingly small amounts of light. We need high sensitivity. And that signal to noise in the measurement will decrease as a function of the area, the open area of the apertures, since the infrared beam is blocked proportionally. So if we go back to the example of the hair, about 0.04% of the beam is occupied by the hair. The frontier, as an example, achieves at minimum a 15,000 to 1 peak-to-peak signal-to-noise ratio with a 5-second scan, meaning if the apertures are fit to the sample, performing a 5-second scan, because we're blocking so much of that light, our signal-to-noise in the resulting measurement would be 6 to 1. It would make it very challenging to get a reasonable or useful infrared spectrum of the sample. Now in this situation, if we need higher sensitivity, we can employ a detector which is called an MCT detector, or mercury cadmium telluride detector. These detectors are approximately 100 times more sensitive than DTGS detectors, and so they're ideal for these sorts of measurements. And these detectors are available in single point or array detector formats. And so the single point detector has one detector element, and the array detector will have multiple elements, either in a staggered linear configuration or in a square array of detector elements. There's other hardware which provides benefit in a situation where infrared microscopy is performed. Let's take a look at these. So of course, systems now come standard equipped with a CCD camera, or charge coupled device camera. And these cameras are highly useful in this sort of situation because, of course, you need to see what it is that you're measuring. In the absence of that camera, you would need oculars so that you could manually view your sample visibly through the microscope. Now, by using that camera, then, of course, the user is presented with the ability to then save that visible image of the sample so that they can record the position of measurement and ensure that the region of interest is actually probed with the microscope. The other critical optical components for the infrared microscope are what are called Cassegrain objectives. And Cassegrain objectives are used in infrared microscopes in place of lenses. So you may be familiar with lenses and how these often have curved surfaces which will focus down a visible optical beam, a light beam. Now in an infrared microscope, of course, you can't send that light through glass, otherwise you lose many of the wavelengths which are critical to the measurement, especially when used for material identification. So Cassegrain objectives are employed. And these are mirrors which have an aluminum coating which has very high reflectance in the infrared range. And the curved surfaces of these mirrors allows them to then focus down the infrared beam with minimal light loss. So now let's talk a little bit about some key performance specifications of infrared microscopes. I'd like to draw a distinction here between spatial resolution and spectral resolution, as there is sometimes some confusion around the terminology that is used here. Spatial resolution we would use as a representation of the ability to distinguish closely spaced objects. So in the example that I provided previously, where we have 3 different layers of material in a sample, poor spatial resolution would mean that the infrared microscope would essentially just present us with a spectrum representing the 3 layers simultaneously. Despite our best efforts, we would see an infrared spectrum which actually represents a mixture of the materials. With higher spatial resolution, then we have the ability to analyze each individual layer within that sample, and as a result, obtain a spectrum for each layer which represents solely that layer of interest. So this affects the ability to measure data which just represents that region of interest. Now, as we go to the other side, we come to the term spectral resolution. Spectral resolution is the ability to distinguish closely spaced spectral peaks. And so this setting, this instrument setting, or this instrument specification will just affect the minimum width of peaks in a spectrum for a given material. So the spectrum that I've provided there is a spectrum of a polymeric material just measured at multiple resolution settings. So the red spectrum there represents the broadest spectral resolution, where you see that the 2 peaks near 1580 are not well resolved. They're represented as a single broad peak. So in that instance, then we would call that poor spectral resolution or broader spectral resolution. It's important to note that when performing infrared measurements with these sorts of systems, if you go to the extreme of spatial resolution or spectral resolution, there's often some sort of compromise in terms of measurement quality or measurement time, because increasing the spectral resolution of the measurement will proportionally increase the measurement time, because the moving mirror in the FTIR will travel a proportionally longer distance. Likewise, for spatial resolution, as narrower spatial resolution is achieved, there's less light reaching the detector, and also to cover the same area of the sample, a proportionally higher amount of time must be dedicated to the measurement to capture each of those individual points or positions in the stage. So let's talk a little bit about sampling modes, which are available on infrared microscopes. Like an FTIR bench, an infrared microscope can be configured for measurements using various sampling techniques. Transmission measurements can be performed with thin samples or excised material which has been isolated. Now, once it is isolated from the substrate or from the product, then it can be transferred to an infrared transmissive disk, such as a potassium bromide or KBr disk. In some instances, a microtome is sometimes employed to prepare a thin section of the sample for transmission measurement as well. Microtomes allow users to cut samples to a tightly controlled thickness. The next sampling mode, which is oftentimes available on infrared microscopes as well as the Perkin-Elmer spotlight microscopes, is specular reflectance. Specular reflectance measurements are useful for analysis of residues and thin coatings on metal or reflective substrates. Very thin layers can be detected because of what we call transflectance, where the infrared light actually makes 2 passes through that coating or that residue. Thirdly is micro-ATR measurement. So micro-ATR provides many of the same benefits as with FTIR bench measurements, in that materials can be tested with little or no preparation. As a result of this, then the sample material can be thick, it can be analyzed on what is otherwise an infrared opaque substrate, which may also be non-reflective in the infrared range. So as an example, if you have a coating or paint which is on a polymer substrate, that polymer will not be highly reflective in the infrared range, and so performing a specular reflectance measurement with that material may prove to be challenging. The micro ATR measurement, because it's a surface technique, then allows the user to actually probe that paint despite the poor reflectance of the polymer substrate beneath. Also, if that polymer substrate is sufficiently thick, if it's on the order of hundreds of microns, it will be very difficult to even get infrared light through that substrate. And so micro ATR offers some key benefits. So in the diagram at left, we see the change in the configuration of the system, moving from optical measurement, where the crystal is raised clear of the infrared beam and clear of the sample. When a micro ATR measurement is performed, that crystal is lowered into the infrared beam to the sampling position in contact with our sample. The image at right shows this very same device on the Spotlight 200 infrared microscope offered by PerkinElmer. We have a unique sampling mode for the Spotlight 400 infrared microscope, which is referred to as ATR imaging. With ATR imaging, this is used to acquire the highest resolution infrared images, which are only achievable due to the high refractive index of the germanium crystal. This crystal is clamped to the sample for the analysis, and during the course of the measurement, the crystal and the sample are both moved through the infrared beam, stitching together an image. And that image, each pixel actually is a distinct infrared spectrum. So users can view sample chemistry, distribution of materials with very high detail. The images below show the ATR imaging crystal. The left image shows the crystal before it is clamped on a sample. The image at right shows that crystal clamped in place on a sample in the infrared microscope. Now for a brief summary of the PerkinElmer infrared microscope portfolio. The Spotlight 150 is equipped with a manual stage and single point detector, so this system is useful for point-and-shoot measurements of samples, helping users to characterize debris, fibers, or samples with a single or a small collection of areas of interest. So this is useful in situations where perhaps debris has been isolated, perhaps with a filter, perhaps visually and manually separated. Moving to the next system in our portfolio, we come across the Spotlight 200. The Spotlight 200 is also equipped with a single point detector but has an automated stage. This allows users to perform automated measurements of many areas of interest individually, as well as performing line scans or 2D map measurements to characterize variation in sample chemistry across 1 or 2 dimensions. So this is useful in situations where customers are presented with a challenge. What are these layers or particles? Where are they? The CCD camera provides the user with the ability to identify multiple regions of interest. And actually the software offers an algorithm which can be used to suggest areas of interest in situations where a large collection of debris or areas of interest are presented to the microscope. Moving to the next infrared microscope in the PerkinElmer portfolio, we come across Spotlight 400. The Spotlight 400 is equipped with the patented duet detector. This duet detector incorporates a single point and a 2x8 linear array within the same dewar. The single point detector is useful for point-and-shoot analysis or applications where spectral bandwidth is critical, while the array detector allows users to cover a large area with greater speed, since at each stage position, 16 spectra are measured simultaneously. This can also provide an analysis in a sort of dragnet fashion, where the user needs no prior knowledge of sample composition or chemistry, and regions of interest don't need to be visually distinguishable. So let's see where the rubber meets the road. I have some practical examples I would like to share with you demonstrating the capabilities of the infrared microscopes. So in this example, we'll analyze a packaging film defect. So this packaging film was a single layer of polymeric material. That single film consists of polystyrene, and a mineral additive. Cosmetic flaws were noted visibly. So as the film comes from the production line, circular pimples on the surface were noted. The presence of these pimples causes that film to fail the quality standards of the manufacturer. To get answers and insight into the cause for these pimples on the surface of the material, then the sections of film which contain these particles or these defects were cut from the film. The material was excised from these pimples and transferred to potassium bromide window for transmission measurement. So let's look at the infrared spectrum. At left, of course, we see the visible image from one of the particles which was excised from the material. At the right, we see the transmittance spectrum of one of the particles. The spectrum provides us with several pieces of useful information. For one, we observe a sloping baseline and offset. This is typically observed with materials having uneven or rough surfaces, and it's exaggerated by materials with a high refractive index. Second, we see some weak bands representing the polystyrene polymer. The plastic has encased or permeated this defect, causing detection of a small amount in the measurement of the debris. And lastly, we come across this intense and broad spectral band at the low frequency side of the spectrum. This spectrum here, or this prominent feature, is actually the spectral feature of titanium dioxide. So how is this valuable to the user? This is an important question to always consider when looking at analytical instrumentation. What does this mean? Yes, we expect to see titanium dioxide in the product because we're adding it as a raw material. Now consider a situation where we don't have access to a compositional measurement. In this scenario, we might assume that particles were purge material. Maybe we assume that the particles were foreign material. In either case, we might expect these defects to stop. The material should clear from the production system, and then we'll go on to having defect-free product. However, without that compositional measurement, we don't have enough insight to make effective changes to the process. And so as we wait for debris to clear the system, we accumulate waste and rework material. And ultimately, that affects profitability. Going to our second example now. Here we're analyzing a multi-layer film consisting of ethylene vinyl acetate and other layers I cannot reveal for proprietary reasons. Cosmetic flaws were again noted visibly in this film where circular pimples appeared on the surface, and once again, the film does not meet quality standards. The material was then excised and transferred to potassium bromide for transmission measurement. So in this measurement, we perform infrared analyses of multiple positions with multiple pieces of debris. In each of these images, then we'll see a red crosshair at the center. This marks the center of the image and the center of the infrared aperture position. Also, you may be able to see a dotted line box centered around that crosshair. This shows the dimensions and rotation of the apertures. So here we have three particles or three regions of interest which were tested with the Spotlight 200. So for each of these defects, we get an infrared spectrum. We see them stacked here for sake of comparison. Now, a quick glance at these infrared spectra reveals a high degree of similarity. As a result, we might conclude that the defects do not appear to be caused by foreign material. A closer inspection of the data reveals some changes near the methyl and methylene deformation peaks, where we find that they are of greater relative intensity when compared to the carbonyl and CO single bond stretch in the gel samples than in good film spectrum. These spectral changes clue us in to the cause for the appearance of the defects. As polyethylene vinyl acetate decomposes, it releases acetic acid. Elimination of this molecule from the polymer structure explains the lower intensity of the carbonyl and CO stretch relative to the other spectral features. So the root cause of these defects is likely decomposition of the polymer material due to overheating rather than foreign material. So here we see a molecular representation of that degradation process. At left, we have the ethylene vinyl acetate polymers. As the material is overheated, then that polymer liberates acetic acid. In our next example, we'll look at a particulate defect identified inside of an aluminum beverage can. Cans like this are coated on the interior to prevent corrosion of the can, which would affect shelf life, product quality, and safety of the product. The microscope actually picks up 2 beams of infrared light from the sample. A portion of the incident light is reflected by the surface of the coating, while some of the light passes through the coating, actually making 2 passes through the coating material. This is the transflectance phenomenon I referenced earlier, and this provides useful information as we'll see in the next slide. So the measurement process includes measurement of the background using a gold mirror as a reference, and the sample spectrum is then performed at multiple regions on the inside of the beverage can. Here we see 2 of the spectra which were acquired with the beverage can sample. The red spectrum was acquired in a region where the coating was free from the defect, while the black spectrum was measured at the position of the defect. Let's look more closely at the spectral data shown at the right without any processing. These are the spectra as measured with the system. Note the slope in the baseline of the spectrum measured at the defect. This indicates scattering of light, typically by an irregular or rough surface. Secondly, note the broad sinusoidal baseline artifact. This is typically called a fringe pattern and is the result of the measurement of 2 interfering rays of light, as described on the previous slide. The frequency of this pattern provides insight into the thickness of the coating. For thinner coatings, the spacing of the peaks and troughs will be broader, while thicker coatings will cause narrower spacing of the peaks and troughs. In comparing the frequency of the fringe patterns, we find that the coating around the defect has been made approximately 10 to 15% thinner. Note that we still observe spectral bands of the coating at the position of the defect, so the coating has not been eliminated or displaced by the presence of the defect, and no additional spectral bands appear in the measured data. This means that the particle is likely either carbon, like char, or metallic in composition. In our last example here, we'll perform an analysis of a microwavable spinach bag. Now this may seem unremarkable, but these products are actually comprised of multiple layers. Each layer has a functional reason for inclusion in the finished product. Here, sample preparation involved clamping in a laminate holder. The sample was actually cut to expose a cross-section, and the film was placed in the ATR imaging accessory held within the clamp. On this slide, we see the visible image of the cross-section of the sample, looking at it from the edge, as well as the infrared image. As I mentioned before, the infrared image contains pixels where each pixel is actually a distinct infrared spectrum. So as we take a look at the spectra pulled from this infrared image, we can see that each color here represents a different material. So the false color process, which has been applied to the infrared image, was applied using our show structure process. This actually performs a principal component analysis and assigns different colors to the most significant spectral features or changes across the infrared image. So we find from these infrared spectra that the bulk of the film is comprised of polyethylene terephthalate and polyethylene. If we look a little closer at the data, we get a little more information. As with many consumer products and packages, this bag contains titanium dioxide as a whitener. This layer can actually be visualized from the infrared spectrum by changing the basis of coloration for the image. Instead of applying false color with chemometrics, we set it to show the intensity at 716 reciprocal centimeters, where absorbance from titanium dioxide increases, but with less interference from the methylene chain rock mode at 710 reciprocal centimeters. The dark orange color in the image at right shows the layer which contains titanium dioxide, whereas the surrounding lighter yellow-orange layers are only low-density polyethylene. You will note an intense red and white layer towards the right of the film due to the polyethylene terephthalate layer, which has strong absorbance at 716 reciprocal centimeters. and one final layer present in this sample. This layer is actually the linchpin of the product. It's an amide-based adhesive layer which holds the outer polyethylene terephthalate layer to the inner low-density polyethylene layers. Once more, we change the basis of coloration, now changing this to the amide 2 band near 1523 reciprocal centimeters. Now the infrared image shows the hottest colors, as we might refer to it, where this band is most intense. We can also see that the thickness of the layer varies a bit along the imaged length of the film. Let's take a closer look at the data to determine the maximum thickness of this layer. The Spectrum image software allows users to draw a line across an image, plotting the ordinate value, or in this case peak height, versus the distance along that line. If we draw this cross-section line across the thickest part of the amide layer, we obtain the profile shown to the right. Taking the difference in coordinates at half height of the peak, we find that this layer is approximately 5 microns thick. So let's review the benefits of infrared microscopy and cover some conclusions we might draw from these application examples. Spatial resolution is critical in targeted compositional measurement in areas where our sample or region of interest only occupies a small space in the sample. In addition to that, compositional measurement provides added insight for root cause analysis. Without compositional measurement, we are making some critical assumptions about the cause for failure of products. PerkinElmer's Spotlight systems offer a range of capability that can help to address the challenges presented by the smallest defects we see in our samples. With that, I'd like to thank you for your attention and attendance for this session, and I'd like to turn our discussion back to Jerry. Thank you.
Well, thank you, Ryan, for such an informative presentation. Before we get started on the question and answer session, I'd like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of the presentation window. And our first question is, for packaging applications, are there any special instructions on sample preparation to study laminates?
I have seen analysis of laminates performed in two different ways. One is with the Spotlight 400 using the analogy that I showed, or the application that I showed with the microwavable spinach bag, where that laminate is placed in a clamp and is cut with a razor blade to expose the cross-section. When ATR imaging is performed then on the surface, you can see the layers that are present within that film. And so there is no requirement here for any sort of elaborate sample preparation process. The sample does not need to be encased in epoxy for the sake of the analysis. Now, it's important to point out that ATR imaging, of course, is an ATR measurement, and so contact between the crystal and the sample is very important. So long as there is a preparation technique which is available to present a flat and even surface to that crystal, then a high-quality infrared measurement will be available. Now, the alternative sample preparation approach that I've seen for analysis of laminates is with our Spotlight 200 infrared microscope. And just as a reminder, the Spotlight 200 incorporates an automated stage as well, but it's a single point detector in the system. And so for each stage position, the system is measuring a single infrared spectrum. Now for samples like laminated polymers, then to be analyzed on the Spotlight 200, I've seen customers cut a sample at an angle so that it is sort of a cross-sectional analysis but with angular interfaces. And at that edge, then line scan is performed moving from the edge towards the uncut portion of the material. And this is a more complicated approach to the analysis of laminates, but it's also a way to get added insight without the requirement of having an imaging-based system with ATR imaging. It does take a little bit more in terms of spectral interpretation to examine the changes with each step of the stage and make conclusions about the composition at each step.
Next question is there any maximum particle size limit for using IR microscopy for microplastics?
There does come a point where there really is not a benefit to using the infrared microscope to for the analysis of the particle. Now, part of that depends on the sampling technique which is used. I have seen examples where transmission measurements are performed with microplastics on a potassium bromide disk. And in that situation, then the upper limit is really the thickness at which the infrared bands which are useful for identification are becoming saturated. So this is a situation where there's so much light loss as a result of interaction with the sample where the user can no longer determine the identity of that particle. But that particle at that point is several hundred microns in terms of size, and so can actually easily be transferred from that potassium bromide disk then over to the FTIR bench, where an ATR accessory could be used for a macro measurement. So really, there is not really a practical limit to the upper size, just that you would move it from the microscope to the FTIR bench.
Next question is, let's say I receive a paint chip with multi-layers, translucent coating, dark coatings, and one epoxy layer. How accurate can I measure this system or similar systems?
So something that I would suggest here is that the cross-section be taken of that paint, because that would require, to get detailed analysis of layer thickness here, the paint would need to be presented to the microscope in a cross-sectional format. And it would help in this particular instance if that paint is embedded in epoxy, because to achieve good contact with a harder material, it's likely that the ATR imaging crystal would need to be pressed to the sample with a little more force. Without that support from surrounding epoxy, then the sample itself may actually be damaged by that added force. So the Spotlight 400 infrared microscope can resolve somewhere in the neighborhood of 2 to 3 microns in terms of layer thickness. And then below that, the intensity of spectral features of that layer within the material then just become blended with spectral features of the surrounding material. We do actually have several customers who are also using the Spotlight 400 for analysis of coatings and paint, as well as in particular automotive samples.
The next question is, what other applications exist for the food market?
So I just recently produced an application note for analysis of debris in food ingredients, and we had an account come to us not too long ago with some filters which were used above their ingredient handling system. And to eliminate the incidence of debris, of course, in the food ingredients, they need to know what the debris is. And so debris was transferred then from the filters, which were in line with their vacuum system. We transferred them to a diamond compression cell to flatten out the particles and fibers, which we identified there, and then performed infrared measurements to determine the composition of the material. So we did find that in those particular instances that there were polymer fibers, polyethylene, polypropylene, polyethylene terephthalate, which presumably came from either uniforms of those in the handling area or potentially from packaging as well. There were some cellulosic fibers and then proteinaceous fiber, which might be an insect wing or leg. So you get a very high level of information from the infrared measurement of those pieces of debris.
Next question is, how would you enhance the signal of a thin film 10 to 200 nanometers compared to the substrate?
So when working with very thin layers or coatings on material, oftentimes the angle of incidence is changed. And so for a measurement of a film which is on the order of nanometers thick, then a shallower angle of incidence, or moving towards, say, like 80 degrees angle of incidence, would provide added sensitivity. And in some situations, then also an infrared polarizer is placed in the beam path to accentuate the light which is interacting most with the surface.
Next question is, in your KBR transmission example, couldn't that have also been done using low E glass slides in the reflectance mode?
They can, yes. So that debris could have been transferred to low E glass slides and then performing a transflectance measurement. So the light would have made two passes through the material. The limitation there in transflectance is that your path length is doubled. So transflectance offers higher sensitivity for thinner coatings, but also you run into the upper practical limit for spectral measurement with a thinner particle than you would in a single pass in a traditional transmission measurement.
The next question is, the Raman spectrum also detects different types of bond vibration. So should Raman and FTIR produce the same results when looking at the same sample?
That's not necessarily the case because some vibrational modes are active in infrared and some are exclusively active in Raman. So oftentimes the situations where users will employ both techniques are those where the user anticipates coming across a material which is a very weak absorber in the infrared, say an organic sulfide where bonds to sulfur are not particularly strong unless it's a hydrogen-sulfur bond, or in a situation where someone needs a conformational measurement for determining structure of an isomer.
Next we have, can we measure the IR spectrum for textured samples without losing the light?
That all depends on how the measurement is performed. So if you're trying to perform a transmission measurement, and if you have an FTIR, this is very quick and easy to demonstrate to yourself. If you take a sheet of paper which is relatively thin, or even a material like a Kim wipe, and put that in the infrared beam, you'll see that the paper, the Kim wipe itself, is very fibrous. You'll see that the infrared spectrum, if you see a spectrum of the paper at all, a usable spectrum, you'll see a very high baseline, and you'll see, of course, some very intense peaks. And that's because the fibrous structure of that material scatters a lot of the incident infrared light. And so a non-uniform surface can present a big challenge for transmission measurements. And in that example, you probably want to lean towards an ATR measurement, whether it's micro ATR or ATR imaging.
The next question is, which minimal microplastic size can we expect to determine using the Spotlight 400?
With the Spotlight 400, that all depends on, I guess, how you would define identification, in that if you need a precise measurement of particle size from the infrared image, that there is a lower limit which you would achieve there simply because of spatial resolution in combination with whatever sampling technique you employ. And so for a reflectance or transmission measurement in air, the lower limit tends to be somewhere around 10 microns, depending on the wavelength that you're looking at. And so for particles smaller than 10 microns from an infrared image may still look as though they're around 10 microns, but you may see a lower intensity of the infrared spectral bands over that area.
This is a similar question. What's the smallest spatial resolution for the Spotlight microscope? it looked like something like 5-micron pixel width, but can it go smaller?
So the spatial resolution of the system, any of the spotlight microscopes, is a function of sampling technique as well as the hardware itself. And so the lower limit is somewhere in the neighborhood of 2 to 3, but again, it is also actually a function of wavelength. And that would be, that example is also with ATR imaging. So in air, measurements in air, you bump into the diffraction limit. And so you cannot focus infrared beams infinitely. And so the ballpark limit to resolution there would be around 10 microns.
Well, unfortunately, we're out of time. I want to thank the audience for attending and for participating in today's event. I would also like to thank our sponsor, PerkinElmer, for making today's educational webcast possible. We would like to ask everyone in the audience to participate in a brief survey from our sponsor. You can see the survey to the right of your screen. You will receive an email alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. Thanks to all for joining. We'll see you next time. Goodbye.